Hi everyone, welcome to the preview of Lecture 1. In this preview, I'm going to go through part of the interleave ADC architecture and background. So here shows the time interleave ADC architecture, which consists of N channel, where you get an analog input V in and a digital output D out. These N channels are identical to each other, and they sample and operate in a time interleaving manner. Well, you can see later on, the interleaving clock can be overlapping or non-overlapping during the track time. So what is the difference between the overlapping and non-overlapping? So that will be explained in the later slide. Well, there's also some advantage of this interleave architecture. Obviously, this is very high speed because the speed is increased proportionally with the interleaved channel. Well, the other is the power is very scalable because each channel is identical. And when you increase the speed, the power is also increased just proportionally. Well, finally, it is effective to have a advanced technology. The reason is because with advanced technology, the channel area actually is smaller so that you can have a more compact interleaver architecture with better efficiency for high speed. But of course, there's also some limitation. So we mentioned that this channel actually is identical to each other, but in the reality, during the fabrication non-ideality, there exists some mismatch between this channel. This mismatch contain gain, offset, bandwidth, and corkscrew. Well, the other not so obvious limitation about the interleaving ADC is the input loading. So imagine we want to have a higher speed ADC. We also want to capture a wider input bandwidth. In that case, if you interleave a lot, you have a large input loading to the front end input. So if you have to design a driver for this front end, this could limit your bandwidth. So here a few remarks about this kind of topology. So interleaving actually can be applied not necessary to the full ADC. It can be applied to the building block. Let's say you can apply to the sampler, you can apply to the comparator in the ADC. So that's why you will see some so-called partial interleaving or alternative comparator. So this is also very similar to the term like ping pong. So indeed, this is more like a 2 times interleave kind of algorithm. Well, if you hybrid a time interleave ADC with the other architecture, we usually don't consider this is a hybrid ADC. So we just consider this is the time interleave, that kind of ADC. All right. So this is not really a hybrid type of kind of technique. Well, here's come a specific example with 4-channel time interleave ADC, and we will go through the operation one by one. So again, we have analog input, digital output, and your analog input is more like a sine wave over here. And you have 4-channel, so these 4 core actually is interleave and without overlapping. So during the first channel is sampling, then the phi 1 is enabled. At the falling edge of phi 1, the sample and hold circuit of channel 1 sampled the input voltage, and the sample and hold output is V1. All right. So during the second channel is sampling, phi 2 is enabled, and during the falling edge of the sampling clock of phi 2, then you sample the V2. Of course, it depends on how you implement the sample and hold circuit. The sampling instant can be defined by the rising edge or falling edge. But as the NMOS is always have better mobility than the PMOS, so usually we use the NMOS to define the instant, And here we assume the falling edge will be the define of the sampling time. All right. So in this case, we have phi 1 and phi 2, phi 3 and phi 4 as the interleaf manner, and sample their input voltage interleaf in interleaf manner. So for the master clock phi m, we have the full speed, which is at the sampling frequency. For phi 1, phi 2 to phi 4, they are operating at the quarter of sampling frequency, which is ff/4. Well, here's also a non-overlapping track time example. Later on, we can see the overlapping track time. All right. So this overlapping track time means you still have the same time, same sampling instant. All right. The moment is the same. However, the track time actually is extended so that there will be overlap track time between channel. So now let's see what is the problem of this overlapping. Well, with the non-overlapping time, you have an input loading capacitance is around the sampling capacitance of each channel, CS. So your input loading will be just CS because you have non-overlapping here. Well, the good thing is with a short track time, then you will have a long quantization time. So you can quantize with, you can have more time for your conversion, right? Well, but the bad thing is because you have to limit your track time with non-overlapping scheme, so the track time is relatively small. Well, when you have the overlapping architecture, so you will see that will be a 2 times of the sampling capacitance. All right, so this is one of when channel 1 is seeing this CS, you're also seeing the channel 4 CS. All right, so that will be where these 2 CS come from. Well, of course, by that you will have a shorter track time and a shorter conversion time, but a longer track time over here. So we all know that for a high-speed sampling, the time constant will define the sampling accuracy, right? So in this case, the T, which is the track time, over tau, which is the sampling time constant of your sampling switch, will be equal to the T over R on times C in. So remember, with non-overlapping, the C in is only CS. With overlapping, the C in actually is 2 CS. So assume we have the same on resistance. In that case, for the overlapping scheme, you will have larger loading. But at the same time, you also have a longer track time. So these kind of counteract each other and make the benefit of the overlapping with more track time less effective. All right. So the other problem of the overlapping is the time varying channel node. So as the example we saw before, so during the initial tracking of the channel 1, you will see the channel 4 sampling capacitance. Well, at the end of the tracking of channel 1, you will see another sampling capacitance, which is from the channel 2. Right? Imagine they are actually at the different condition and with different kicking charge to the input. That actually may ruin the sampling linearity of channel 1, especially when during the end phase of the tracking, while the time instant actually is very critical, then you have another kicking coming in from channel 2. So this will actually affect the linearity. So that we conclude that could be a crosstalk or a kicking from the other channel. With this effect, you will see actually there's a spur rising at the spectrum. So in the spectrum, you will have a lot of spur, which is not easy to identify because they are from the kicking from the different channel. So by that, actually you will need a very low impedance or high driving capability buffer to settle those errors. Otherwise, this bird will even worse, like the kickback error from the whole ADC. All right, so here's come to the end of the first preview. I hope you guys enjoy this part, and we will detail a little more when we talk about some of the time interleave ADC non-ideality, and then we talk about different architecture consideration while you have direct interleaving and hierarchical interleaving, so on and so forth. Okay, so thank you very much.